The green theorem states that the integral of a vector function f over a closed bounded region R given in the xy plane can be evaluated as follows. We have a double integral over the bounded region of the partial derivative of the f2 over x minus partial derivative of f1 over dy times dx dy. So this will give us the integral of the given function f evaluated in the closed bounded region R. However, we can also integrate or obtain this result as the line integral of the closed bounded region, what now is the region C, that this specifically is the contoured region, if we can say. So maybe if we have this region R, C will be this contour that we have of the region R. So now the integral will be evaluated as this. So just notice that this can also be wrote as the line integral given as this, as we were previously talking, given that f is actually f1, f2, and dr is dx, dy. Hence, we get this result using only a line integral instead of a double integral evaluated at the closed bounded region. This important theorem allows us to, instead, as I was saying, of evaluating a double integral, use just a line integral to obtain the result of this evaluation. However, other important characteristics of this theorem can be used in order to obtain other kinds of results. For instance, if we have that f1 is equal to 0 and f2 is equal to x, given that f equal to 0, x, we can say that this function evaluated in a closed region R is equal to the derivative of f2 with respect of x, that will be 1, minus the derivative of f1 with respect of y, that will be 0, times dx dy is equal to the integral of a closed curve C with f1 dx, that will be the derivative of f1 with respect of x at 0, times dx plus f2 x times dy, that will be equal to the double integral over the bounded region of dx dy equal to the integral in the closed curve of x dy. And now if we have that f1 is equal to minus y and f2 is equal to 0, hence we have f equal to minus y, sorry about that, comma 0, then we will have the double integral over the closed bounded region of the derivative, let me divide this, of f2 with respect of x, that will be 0, minus the derivative of f1 with respect of y, that will be minus 1, times dx dy is equal to the line integral over the closed curve of f1 times dx plus f2 times dy, and this will be equal to the double integral of dx dy equal to the line integral of the closed curve of minus y dx. So saying that this is 1 and this is 2, we can then add 1 plus 2, and this will give us dx dy. Sorry about that. Over here, dx dy plus dx dy equals the integral over the closed curve of x dy minus y dx. Hence, we will have 2 times the double integral equals the line integral x dy minus y dx, and hence we will have that r dx dy is equal to 1/2 of the line integral x dy minus y dx. And this can also be interpreted as the area of the given closed bounded region. Then we can obtain a formula for calculating the area of a closed bounded region, given as this, only using a line integral x dx, x dy minus y dx. But also, we can make this using polar coordinates. So we know that x in polar coordinates is equal to r cosine of theta, and y is equals to r sine of theta. Alright, so we know that dx is equal to cosine of theta dr minus the sine of theta times r d theta, and the derivative of y will be sine of theta derivative of r plus cosine of theta r d theta. And if we use the formula that we obtained previously, we can get that the area is equal to 1/2 of r cosine of theta times dy sine of theta dr plus r cosine of theta d theta minus r sine of theta times dx. That will be cosine of theta dr minus r sine of theta d theta. Okay, now making some algebra here, we get r sine of theta cosine of theta plus r squared cosine squared of theta d theta minus r sine of theta cosine of theta, here we see the r dr plus r sine squared of theta d theta. Following up with this algebra, that the area is equal to 1/2 of this minus this is 0, so we only have this summatory of these two, and that would be, sorry about this is squared, r squared of cosine of squared of theta plus sine squared of theta times d theta. However, this is 1, and hence the result will be 1/2 of the derivative of the closed bounded region. Sorry, it's not the closed bounded region. This is the closed curve line integral of r squared d theta. Hence, we can get yet another form of calculating the area of a closed bounded region using the polar coordinate representation of the curve. So there it is, and that's the importance of the Green's theorem and how it can be useful to calculating the area of regions.